All right, continuing with Introduction to Laplace, Part 2, and we're going to continue looking at properties that we need to discuss. So last time there was a list. Here is that list, and we finished last time. We went through linearity, and we went through scaling. These are a lot like, associative and multiplicative and distributive laws, these kinds, same sort of thing going on with Laplace. And then we looked at shifting, both with time and with frequency. Okay, so now we want to catch up, go further on with time in particular, and we'll look at three properties of it: differentiation, integration, and periodicity. And then finish with frequency differentiation, and then of course getting initial and final values, pretty important. All right, so time differentiation, and we start with the Laplace of a particular function, right? And we do that. Here we are written as the Laplace of a differential of the function, and of course it is turned on at the unit function, the step function of time, and this is to keep us all in the forward plane, right? So this is just filled out. If I want to take the Laplace, I have to, the unit step makes us from 0 positive out to infinity, and here is that. Now, it turns out if we're going to work with this successfully, we're going to have to get into a little more math, as I've cautioned you. And the math we're going to talk about here is integration by parts. Not too hard. It really reduces to a formula. You just need to be real careful with, choosing your parts. So integration by parts really amounts to, after the derivation is done, the formula of u v minus the integral of v du. And I'm looking like a W, but it's not, it's v du. Okay, so the trick is, in all of this, this u is not this u. Okay, this is the step function. This is a u of t that's not the step function. This is just standard terminology you'll find any place you look it up, probably in this book, certainly on the web, in reference books that I've got. They always write the formula as, the integral of df times e to the minus st dt, the integral of two functions where one is a differential, breaks down to this in integration by parts. See, uv. So we're going to have to identify two functions. More particularly, we're going to have to identify a function and a differential that work. So sometimes it's just testing. In this first case, we're saying we want the Laplace of the differential of a function, and this is that setup. So we're going to start with u, pick the function u is equal to e to the minus st. Okay? And then we're going to pick out a differential dv. See, so the trick is you pick out one function, but then you have to pick out the differential of the other part. And in this case, it's going to be df dt times dt. Okay? So to integrate this, and we're doing integration by parts, as the name says, we're going to collect this guy with this guy, and identify that as dv. And then we're going to take this guy and identify that as the function u of t. So in the integration by parts formula, that's what we've got going. And to fill out what we want, we're going to need a uv, and then we're going to need a v du. So we really need all four parts of the two functions. So if u is this, right, then du, which we're going to need here in the formula, is equal to what? Take the derivative of u minus s e to the minus st dt. Okay? And if this is, it's unfortunate they chose u and v. At least it's unfortunate for people with penmanship like me, where you get in a hurry and the u's start to look like v's. Now, so if this is dv, right, then v is what? V is just simply some function of t. Okay, so we got these four things, all of which are going to match up with the formula. Here's u and v, and then here's v du. Okay, so when we do this, we plug it into the formula. We're going to get this. Okay, so let's identify what happened here. This is uv, right? And now notice we have to evaluate it because it's as though it were integrated, right? And we need to evaluate it at the beginning and final values. And the u of the step function, that u of t, assures us that we're going to be starting at 0, right? And we say 0 minus, everything turns on just before that. The second part, so here's our minus, and here we've got v. Where's v? V du is this. See, there it is. There's our du dt. So this is du, and this is, right, this one here is just v of t. Okay? So all of that is just straight plug, and then we'll do the chug now to keep this going and start evaluating it. All right? So in the evaluation, so all we did between here and here is we're going to evaluate this lower bound, right? So the function at 0 is just f of 0, right? But that's a lower constraint, so it's minus that. And then it'll be plus f of infinity we don't know, but e to the minus infinity we do know. That's 0. So this is really the evaluation at infinity, and this is the evaluation at 0 minus, right? And so that just plays to the formula, and we get that straight away from the formula. Okay, now the second part evaluates to what? We're plugging in, we get we get the integral. They sort of squirreled over it. This is not a bracket, it's an integer. And we get, pull this out, minus s times a minus is plus s, e to the minus st f of t dt. Okay? But this whole thing here, whoop-de-doo, this whole thing integrates to this, right? Because at infinity, once again, the upper bound goes to 0, and all we are left with is, well, there is the upper bound. That's our Laplacian, sorry, and there's our lower bound stuck in here. Okay, so that's the evaluation of that, and in pretty terms, it always comes out to this, right? So this is, I would say, as you move from here to here, this is what I would call nice. A nice, simple arrangement that takes advantage of integration by parts. Okay? Now let me I'll just draw a line under that because I want to look at further derivatives. We only took the first derivative here, right? So if we go a step further and try to take the second derivative, all right, well, that's going to be just a continued operation on the first derivative. So you can complete the first derivative. We did that here. We did that up here. Whoops. And we can apply this same thing again. Here we've done it, right? There it is, the first derivative. The Laplace of the first derivative. We might call this f prime, or f1 of s, the first derivative of s. So we multiplied it by s, took the Laplace of that, right? There was our original. Comes over to this. And now we take the Laplace of that. Oh, but now we've got a formula for that. So we can take s times our first derivative here, this whole thing, right? Plugs right down into there. Take it times s and subtract the evaluation of the first derivative at 0 minus. Okay, so that's how we can get it. And you can imagine now the process can go on and on. Here that is in pretty form with the 2 marks now. And if we wanted to keep that going to the nth derivative, we just keep that process going. And we get this sum, this kind of a series that develops. All right? So let's, I'm going to draw, where am I at here? I'm going to draw another line to separate that and just do an example. And the example is, back to the beginning, f of t is cosine omega t, and there's our step function to make sure we're only interested in the positive part. Okay? Now, we can do that. Well, I should back up first because that's where we're going to head. We're gonna say, so we need to say, so the f of 0, the cosine, if we think about the cosine, what is the function at 0, right? We've got a look-see at the function, and it's like this, right? So this point is that, so that's 1, okay? And we also know that the f prime of t is equal to, if I take the derivative of this, I get what? Minus omega cosine, well, stop there, sine of omega t, right? And the u of t comes along. All right. So now what we're really achieving is, if we take we want the Laplace of the first derivative of cosine, we would be getting the Laplace of the sine. So here that is, the Laplace of the sine is minus 1 over omega times the Laplace. Why have I got this? Right, because that's going to be, right, we want the Laplace of the sine, so we've got to multiply the f of t, right, 1 over omega times f prime of t is the sine of omega, right? And we want to find the Laplace of this. And so to do that, we're taking minus 1 over omega, and we're going to do our Laplace of the derivative of the original function, which was the cosine, because we have the Laplace of that. So here that is. So the Laplace of sine omega t can be converted to -1 over the Laplace of the derivative of some other function. And if we know the Laplace of the cosine, this tells us we can quickly get the Laplace of the sine. So here, let's do it. Here's the Laplace of the cosine. There's that thing right there. And so we're going to take s times it, and then -1 over omega times that. And our initial value is -1, right? We figured that out over here. Oh, come on. Figured that out over here. So if I do all that, I get what? -1 over omega. If I expand all this, I get what? S squared minus S squared minus omega squared, right? The numerator becomes, let me put it together, S squared minus S squared minus omega squared. And the denominator will be S squared plus omega squared, right? And I'm going to multiply this whole thing. So these go away. They cancel. And remember, this is multiplied by -1 over omega. Yeah. And so that ends up minus, cancels minus. Omega squared takes away one of these. And I get to exactly this, right? And that tells me if I only had the cosine, I could have figured out what the Laplace of the sine was. And we did this in an earlier section, and indeed this is the Laplace of the sine then. Okay? So we use the example just simply shows how you can convert from one to another. When we knew both sides of it, it was just, sweet to look at. But the idea, the extension of this is that with this simple formula here, this simple way of handling it, this nice way of handling it, we can take a known and transform it into an unknown, into something we desire. Okay, with time integration, our next property, what we want is to take the Laplace of the function between 0 and t. Okay, last time we did the Laplace of the differential. So that's what we want. And that equals the integral of an integral, right? So if we recall, here is our basic function that we want the Laplace, whoa, not that far out, that we want the Laplace of. All right, and that's done by taking the integral of it from 0 to infinity. Notice this is from 0 to t, e to the minus st dt. So this is what we want, okay? And to achieve this, we're going to have to, it's an integration problem for us, so we're going to go back to integration by parts. We've only got, right, a couple of tricks in the bag here. Integration by parts is going to be the main one. And then the derivative of the product of two terms is going to be another one. So here let's do our identifying our u and our du and v and dv. So if we substitute u equals our target, right? So this is the guy we want right here. And so du of that as a dt is just this, f of t dt. The other half of the substitution, remember we're looking as we substitute, we always are trying to find the u and the dv, and then we'll work our way backwards to the v or forwards to the du, right? So if this is my dv with respect to t, a likely candidate, right, since it contains the other part here of what we need, then v is -1 over s e to the minus st. I just integrate this thing. Okay. So if we have that, then our next step, our usual step, is one of these few things. We're going to integrate by parts. Okay, so let's be refreshed. The integral of u dv. And is that what we want? Here it is, our u, the integral of that. The integral of u dv. So there's all the parts. Here's our u. And this out here is our dv. All right, so the integral of u dv is equal to uv minus the integral of v du. I've always found this one fairly easy to remember because it's just like the differential form. It's something minus, and as soon as you get the u dv, you know the other one is going to be v du. So you really just have to remember the front end of this. Anyway, so we're going to integrate by parts. We remember that, and let's do that. Here's a whole bunch of stuff. So starting with, replaying the problem, right? And here's our integral of f of x dx. So this is our u, and here's our dv. All right. So that's our u. I'm sorry. This is uv. I knew I was wondering over something. That's our uv minus v. Oh, there that is. du. All right, all laid out for us. So just checking, getting the parts, because sometimes in the text, as in most texts, they just sort of name it and then just start blasting equations at you. And for me, I just say as a good learning technique, it's helpful for me to just do like I'm doing here. Just draw in the parts, convince myself that that's really what happened. All right, so what is this now? This is equal to 1 over s integral of f of s, right? We got all this. That's our first part up here, right? But the first part, no, we evaluate that. What have we got? When s is 0, right? When s is 0, because we're evaluating at the limits, we've got 1 over 0 e to the minus 0, right? So that's e to the minus 1. Okay, add this one. These limits are around t. What was I thinking? All right, these limits are around t. So when I plug in t equals 0, I get what? Minus 1 over s e to the minus 0, which is 1. So I get minus 1 over s, right? At the lower limit, this is going to go to minus 1 over s. But then t is 0, so that's going to be the integral from 0 to 0 of f of x dx. But 0 to 0 is going to be 0. So this lower limit at t equals 0 minus is 0. The upper limit of infinity for t, it was then e to the minus s infinity, so 1 over e to the infinity. This is going to force it to 0, right? So both portions of the first part at those limits are 0. So we're left with evaluating the second part, all right? And we're doing e to the minus st, f of t dt. Oh, but we've done that before. We've seen this. So we take out the 1 minus s times minus. So this and this yields this, 1 over s. Now times the integral of ft e to the minus st dt. Oh, but that's f of s, right? So we can express the integral, or the Laplace of an integral of a function, as 1 over s times the Laplace of the function, okay? Very similar now to what happened with the differential, which is it's s times the Laplace of the function itself, all right? So you can kind of see what's going to happen here. Here it is in pretty form. Whenever they change from the color blue to black, it means, all right, this is the point to remember. So the Laplace of the integral of f of x is 1 over s times the Laplace of f of x itself. Okay, straightforward. So let's look at a couple of examples, right? Let's have we're just going to take a string here. This kind of goes in a string, if I can locate where my pen is. So let's have f of t equal to the step function. That's not v of t, or I am with my sloppy u's and v's. All right, and we know that the Laplace of this is 1 over s. Okay? In other words, we already showed that the integral of a step function, or we know this, what's the integral of a step function? It's a ramp. Well, I didn't get a very straight line, but it's a ramp. Okay? So we want to find the Laplace of this, and that will give us the Laplace of this. Okay, so we do that. When we do that, we want the Laplace, and that will be the Laplace of t. T is a ramp, right? This is the function described there. All right. So this is what now? Let's follow it through. That's following our rule down here. Right? We're going to follow this rule. It's 1 over s times f of s, right? Here's the f of s. So this is the Laplace of a ramp. This is f of the ramp. Okay. Well, there's no need to quit there. We often use something that's the second order. So that would be, if we say the Laplace of a ramp, I suppose I could put dt in here to be really fancy, but the Laplace of the ramp is, we're really finding what? The Laplace of the parabola. Okay, so this is looking like the Laplace of, here's our ramp from 0 to t, and that was the Laplace then of t squared over 2, right? This function, this is the result of that integral. And so that's 1 over s. We already have the Laplace of t. So it's 1 over s times s squared. All right, and if we keep that going a lot, we get, right, well, we have to finish this one. We got to deal with this 2 down here in the denominator. Whoops. Right, that guy's got to come out. So the Laplace of t squared by itself, not offset by the constant, is just 2 over s cubed, right? Finishing the math. And if we want to generalize that, the Laplace of t to the n, t to the n here, is this guy. We know what's happening in the denominator. It's just s to the n plus 1. What's important to remember is this is n factorial in the numerator, and why is that? Because each time we do one of these, now we've got 2 over s squared. If we wanted t cubed, right, as an example, right, we know that this is going to have something like t cubed over 3 in the place of this t squared over 2, right? So the Laplace of that, of t cubed over 3, is equal to what? 1 over, we're already at the cubed level, so this has got to be s to the 4th, or n plus 1. Oh, but now we got to get rid, I'm sorry, this was 2 over s to the 4th. And now we bring up the 3, so it's going to be times 3 in order to clear it out of here. So this is a factorial thing going on. N minus 1, n minus 2, n minus 3, so on and so forth. Okay. Then if we want to finish the deal, we have this, right? Notice if we want to get the Laplace on the front side of all of this, right, on the front side, we have the same basic identity happening here. Whoops. There's our 1 over s f of s. But now we've got this term 1 over s f to the minus 1 of 0, because we're starting from way down here and at minus infinity. And so we would have to add this piece right here to bring it up to 0. So this is the part that is from time greater than 0 and less than t, right? And then this is the preceding part, right? So this is the simple modification to the integration form when we want to include the time before 0, which we're not going to be doing. We're not going to be doing here. So let's move on then, and we're going to go on to periodicity. And periodicity is just kind of, at this point, I'm sure what you'd expect. If you have a periodic waveform, here's a simple one just as illustration. We're not going to attempt to find the Fourier of a semicircle. But the point is, you can recognize the period. Here it's t, large T. And you can say, well, that signal is just composed of a bunch of the same signal of period t added one after another. Okay? Well, we could describe that certainly as the sum of a whole lot of parts. Now, we're still in the time domain here, right, over here. I want you to know we're still in the time domain. And all we're recognizing is that this signal we started with can be broken up into these parts. And that's just a simple summation in time. So we're taking f1 plus f2. Notice they're different frequency, they're different graphs. But it's simply the sum of the graphs, where each graph in the non-picture portion, the non-portion of the region of interest, is always 0. So you're not adding anything, in fact, you're just adding the time period of interest. We can represent that in time, we know, by this. We have f1, that stays the same. But we can just offset the basic function in time, right? So we're going to shift it in time and add the unit time function to it to turn it on at that point in time. So it's always this basic element right here, shifted, and we make the time sum of that, all right? And we have that here. So if we go by that, on that term by term, oops, we could just write what f1 of t as f of t times u of t, turn it on, and then turn it off big T seconds later. In other words, right, this is just expressing that f1 of t is f of t over this integral and 0 otherwise. See, so we took this guy and made kind of a turn on, right, a turn on function, and then a turn off function by just subtracting it. That's what's going on there. All right, so now you see the setup, how we're able to express. I mean, you can see where this is going. We're going to be expressing every one of these, f1, f2, f3, in terms of f. And why do we want that? Because that is going to be the function that we have the Laplace of. All right, So that means f of s of the total of the periodic function is going to be here's our main one, and then here's the first shift of it, here's the second shift, and so on. Okay, this back here would be the 0th. All right. So once we have that, so now notice the obvious thing happened, the same thing we were setting up back here. You factor out the Laplace of the basic function itself, the basic period, and then just add all these time shifts, however many you want. Okay, so this is a series going on, right? This is looks like an infinite series, and we know we can represent series by doing series expansions or recognizing the type of series that this is. It's what? One. We're going to have it of the form, where are we here? 1 plus, one plus x, e to the x squared, that sort of thing. So here it is. If x is equal to, quite obviously, x is equal to e to the minus ts. And remember, x squared doesn't give you t squared s squared. It gives you 2ts, right? So on and on it goes. This can all be expressed or captured in the series as 1 over 1 minus x, right? And so this is, so we can say for what? X, the magnitude of x less than 1. Right, if the magnitude of x gets greater than 1, this is going to get negative. But as long as the magnitude of x is less than 1, you get a large number, but you won't get infinity because you won't have a 0 base. And so for that, you can have f of s equals the Fourier of the primary function over 1 minus x, e to the minus ts. Okay? So I think you're probably getting some of the ideas now that to extend Laplace transforms by these various properties, we're really just reusing a couple of ideas. We've had integration by parts and differentiation of a product pair, and then we've had some breaking it out with sums and time delays, so that we always get back to using or reusing the Laplace transform of the basic property. In this case, periodicity. It really becomes clear. We only have to work with one particular function, and however periodic it becomes, we can extend that very nicely. All right, let's move on to frequency differentiation now. We have this, right? We have the integral. So, right, so this thing we got this. Okay. What we want to do is we want to take the differential of this with respect to s. Whoops. The frequency variable, right? We want to do that. In other words, we want df of s ds. All right, and that's the integral between 0 and infinity here. Whoops, something got cut off. Of f of t minus t e to the st dt. All right. Oh, there it comes. I don't know what happened there. But anyway, so if we do the math, we pull out all the various variables. What have we got? We pull out. We come here. And we take this and pull it out. We're going to separate out this. So we end up with our nice usual ending to the Laplace transform. And then here we have minus t, f of t, right? And I think you see this is, we've done stuff like this, so we're going to rely on things we've already done. And so now we're going to be wanting the Laplace of minus t f of t, because this is always the back end of, this right here is always the back end of the Laplace, right? This coupled with this fills out, this is what we want the Laplace of. The Laplace of, okay, kind of an awkward way to spell it out, but there we have it. That's what we want the Laplace of. So the Laplace of t, f of t, we've just shown, is the same as minus the differential of, well, in the frequency domain of the basic function of s itself. So we can differentiate an f of s. That's the point. Okay, we have an f of s, some Laplace function in terms of the variable s, and we're just going to differentiate on s. And if we do that, if we do that over and over, right, we're going to get this sort of thing. Right, and what happens, the minus sign, we're just tracking the minus sign, right, with a power. Each time we take the differential, we want to multiply by minus 1. So that's either going to be plus or minus depending upon the size of n, or the oddness or evenness of n. Okay, so let's take an example where we know the Laplace of e to the minus at, right, is equal to what? 1 over s plus a. All right. Now we're just going to use this formula. Right? We're just going to grab that, come back over here, and use that. And we're going to say then the Laplace. Oh, way down there. All right. The Laplace of t e to the minus at. So now we want the Laplace of this. Here's what we have. It's the differential. There's our f of s, the original f of s. So we're just going to absolutely take the derivative of that, right? So it's the bottom times the derivative of the top. Derivative of 1 is 0, so that would be 0. Bottom times the derivative of the top, right? Plus the top, 1 times the derivative of the bottom. Well, the derivative of s plus a is just 1 over the bottom squared, right? The denominator squared. So that's what we have, 1 over s plus a, the quantity squared. Okay? So initial and final values. The last of the properties section, let's look at this. We can take a look at the differentiation, or the differential time differentiation property, which is really just what's expressed here, right? Whoops. So this is time differential. Okay. We had s, f of s, minus some initial value. So this is the one we're going to try to extract, right? That's equal to this differential property, which is, right, all of this. If we take the Laplace of the differential, that's this. So so what is that? Let's take the limit, since we've got time going to infinity. Let's take the limit as s goes to infinity of s f of s minus f0, right? But the point is, this is independent. This is independent of s. All right. So that ends up 0. And F0 can be expressed as, see, this independence of S will mean this is always, this term is going to always be 0. I'm sorry, not the term. Here, let me get this. Give me a chance to use this eraser function. This isn't correct. The point is, it will, this whole combination, this whole derivative is 0. It's independent of S, which allows it to be 0. And then over here we simply solve for, solve for F0. Right? And that's the limit. So the limit, the point is the limit of SFS minus F0 is the limit of SFS minus the limit of F0. But F0, the limit of F0, is going to prove, is what we're after. The whole thing is equal to 0. So F0 will simply be, solve this equation, the limit of SFS. Okay, let's have some examples then, okay? By the way, that's called the initial value theorem. You've probably already seen that in the text, but there it is. Let's have some examples. Here are favorites, the trig functions, the cosine and sine type functions. So when f of t is e to the minus t cosine of 10t, right? That's the f of s is s plus 2. So we have this. I mean, by the way, what are we doing here? This was the frequency shift property. Okay, where here was the shifting element, and here it shows up here, right? We know that the Laplace transform of cosine 10t is just s over s plus omega squared, or 10 squared. But now if we shift it, we had that whole property of frequency shifting. There's the shift amount is 2. Now, let's not lose track of what we want. We want the initial value here. We want f of 0. And we said, through what we've shown, it's the limit as s approaches infinity of f of s. So let's multiply through by s squared plus 2s in the numerator. All this in the denominator, right? Basically, all we did was multiply that out. And 100 plus 4 out of that gave us this. And then we clear things a bit so that we have, we don't have, I mean, we're dividing or extracting out the s squared. We're trying to get this in something that sort of resembles the standard form, right? So we get 1, 2 over s. We get these parts, pretty straightforward. S squared over s squared, that becomes that, 4 over s, and 104 over s squared. Now, why did we do this? Because s is going to be taken to infinity, and we want to find out and extract any constant terms, right? So now, what have we got? We've got, pretty easily, the only constants are 1 in the numerator and 1 in the denominator. So there's our initial value. Just a great thing. All right, same thing can happen on the back end with final values. Here's that whole arrangement, except now we're looking for same arguments, and we're going toward s equals 0. In other words, we just want the limit as s approaches 0, the other end of the spectrum, and that's this, and we're going to solve in the same way. Okay, so as s approaches 0, let me just remind you, these limits here are limits on t, not s. Okay, so by doing this, we plug in. Now this is s, and we're going to let s approach 0. And so here is that, and it's equal to the function at infinity because e to the 0t is 1. So it's going to be the function at df dt times dt. So it's going to be the integral of df between the bounds of 0 minus and infinity. And so that's going to be the function evaluated at infinity minus the function evaluated at 0. Okay? But we see this same term here, and we see it here. Okay, so those are going to cancel. And we're going to get then the limit, which we'll call the final value theorem, of f of infinity is the limit right here as s approaches 0. Okay, the final value. All right. All right. And by the way, it's important to add that for the final value theorem to hold, the poles must have negative real parts. You can have complex poles, but they must be in the left-hand plane. Whoops. The left-hand plane. And we'll see more about this and where poles lie and the effect they have and the importance of what plane there is. We'll see more and more of this. Let's take a look at a couple of examples, if we might. Now, we know this is true. So here's, we've already seen this. Here is the sine of 5 omega t, but now it's time shifted by 2. So remember, sine was what? It was here's the time shift, and this is the frequency going on here, right? So that's the s over s plus a, the quantity squared, only now we've time shifted it by that amount. Okay. And if we want to find the final value of this, we want this limit of s f of s. So simply multiplying through by s, top, in the top, right, that makes it 5s. Expand the bottom, right, and evaluate as s goes to 0. Well, you've got 0 in top, and you have a non-zero in the bottom, thank goodness. All right, so 0 over something is 0. All right, let's take a look at another case. Here's the sine of t, u of t. All right, so there's our simple expression. There's no time shifting, and the frequency is 1, right? Omega equals 1. So if we apply our rule to this for the final value, we would again get s over s squared plus 1, and we'd evaluate this to be 0. Okay? All right, but it is important to note that this is in violation of the rule for applying the final value theorem, because these roots, if I solve for the roots here, what have I got? I got s plus j times s minus j. All right, so I've got two roots. One of them's in the left-hand plane, and one of them's in the left-hand plane, and one is not. Right, so this is oscillating between plus and minus 1, which we know the sign does. So so all you can say here is that the final value theorem, does not apply. Okay, we'll have to have another way to deal with that. All right. I put this chart in, which is straight out of the text. That shows properties of the Laplace transform as well as the Laplace transform pairs. And we're going to be referring to these in the next lecture. These are actually two tables. This one here is called Table 1, and this is Table 2, nicely referred to in that way. you will see these tables, and you've already seen from the properties the importance of knowing what f of s is for given lots of given basic functions. And look at all that's covered here. Some of these you could have derived yourself. For instance, this, we know this relationship, we know that relationship, right? And we could have derived a lot of those. But handy references, we'll be referring to those a lot in the next lecture. Let me do a couple of practice problems, if I might. There are many good examples in the book as example problems. I encourage you to work through those because they are chosen to illustrate the techniques required. But here's problem 3. Let's find the transform of this function, a cosine. So this is the sum of two functions, right? We've got basic functions we're taking the cosine. So remember what this was when we did one of the properties where we're summing. Okay, so we've got one function and another function. All right, and we can see it that way. So if we isolate those, and we're saying f of t, we're going to scale f of t to 2t. So we're scaling f1 of t, and that will become cosine 2t, right? So we're going to work with the cosine of t function and scale it, right? So f1 of s then is equal to what? Our s over s squared plus omega squared. All right, and so this has already been set up for us. S over s squared plus 2 squared. Okay, it's nice we actually applied one of the properties earlier to get to this. I remember we showed that was the result. Then f2 of s, right, which is our e to the minus 4t. So that, of course, we know is 1 over s plus 4. Okay, so now in terms of our grand properties, we've got fs, the total, I'll just call it that, is what? f1 of s plus f2 of s. Okay, kind of, this is back to what you remember from, high school algebra and such, where you've got the associative, commutative, distributive, and those laws, then the additive laws, and that we've got that same thing going on here. All right, so that's s plus s squared over 4 plus 1 over s plus 4. So let's just crank this out, as so many of these things are. It's s squared plus 4s, I'm cross multiplying, plus s squared plus 4 over the product. S squared plus 4 times s plus 4. Okay, looking good here. There's not a lot. I suppose we could play with this and see if there's something else, just as a factoring exercise, but I don't want to. We end up with this, and our denominator stays the same, right? All that fills in the same. And yeah, that looks like what he's got down here in the answer. Whoops, down there. All right. Okay, so in 15.4, we want to find the Laplace of the product of two functions, t squared cosine 3t. The u of t, of course, assures us that we've got positive only design space, 0 forward. This is actually t times, and we have a property involved here. So if this is our basic function, right, f of t, then we can find t times it using that that derivative property that we've got. So f of t, let's just start with that. F of t is cosine 3t, right? So f of s is equal to what? S over s squared plus omega squared, which is 9. Okay, so this gives us our f of s. Now, we'd like to get the second derivative, right? We'd like, we know that the Laplace of t to the n times the derivative, t to the n f of t will just be minus 1 to the n, right, times the nth derivative of f of s ds, right? Okay, so we've identified our f of t, our t to the n. We know now that n equals 2. So minus 1 squared, that drops out. We're really just worried about finding the second derivative of this function, right? So the first derivative of s is what? The bottom times the derivative of the top, right? We've got the bottom here. So that's s squared plus 9 times the derivative of the top. The derivative of s is 1 minus the top times the derivative of the bottom, which will be what? 2 times s plus 9. I'll get my 2 in there. 2 times s plus 9 times the derivative of what's inside, which is the derivative of s, which is 1. So here we have this all over the bottom squared. The quantity squared. Okay? So we might want to take the trouble to clean this up, since we're going to have to take another derivative of it. So s squared plus 9, that's fine, minus s squared plus 9 times 2. So s squared minus 2s squared, that looks like we're talking about minus s squared. And 9, where are we at here? 9 minus 2 times 9. So that looks like, 2s. We got s squared plus 18s. S squared minus 18s plus 9. Yeah, I'm just thinking here. I did this wrong. I'm seeing, whoops, where's my pen? This is wrong. It was the bottom times the derivative of the top, bottom times the derivative of the top, minus the top times the derivative of the bottom, but it wasn't the squared bottom, it's this bottom, which is simply 2s, right? This is not there. I'll take that out, all right? So now I have s squared minus 2s squared, so that's a minus s squared, plus 9 over s squared plus 9 squared. One thing about all this stuff is, as I've said before, it's math intensive. So now if we want to get, so you just have to be careful. There's just a lot of steps where things can go wrong, as always. So if I want to take the second derivative, apply the same rule. Here's what we've got. So it's the bottom, s squared plus 9, the quantity squared. This is going to get dicey, as you can see. Bottom times the derivative of the top. So that's minus 2s. Yep. Minus the top right, times minus the top. Okay, I guess we could have minus the top times the derivative of the bottom, which is 2 times s squared plus 9 times the derivative of what's inside, which is 2s. Oh boy, just got to watch our step here all the way. Over the bottom squared. So s squared plus 9 to the 4th. Okay, now what can we do? Well, hopefully we can pull a few things out of all this. So here's an s squared plus 9 that we can afford to throw away because we've got one over here as well. So we'll get that out of the way, and that'll reduce this to a 3. Okay, we'll do that right away. I'm not sure how much else we can do without cleaning this up some. So let's do this. That looks like, what have I got here? I got a 2s and a 2s and a minus 2s. Maybe I'll just pull the 2s out and see what happens. 2s times, what have I got? 2s times minus, looks like minus s squared minus 9. All right. And now if I pulled out this 2s and that 2s, left the minus sign. Now I've got 2 times minus minus, that's plus 2s squared. Okay, that accounts for that term. And then I've got 2 times 9 with a minus sign hanging in there. So that looks like minus 18. Don't know where all this is going just yet, but it's something. Over s squared plus 9 to the 3rd. Whoa. So what is this? Well, this comes up pretty nice. The denominator seems taken care of. 2s squared minus s looks like s squared minus 27 times 2s. Well, amazing. That's what he shows for an answer. All right. All right, let's do 15.7, and this is similar to yours, basically the same shape, but from a different text that I copied. So we're going to want to find, right, f of 0, the initial condition, and that's what? The limit as s approaches infinity of s g of s. All right, nothing fancy about switching s to g of s. So in the numerator, this just makes 6 s to the 4th plus 2s squared plus 5s all over. And we don't need to divide this whole or multiply this whole denominator out, at least not yet. But let's write it out. S plus 2, the quantity squared, times s plus 3. All right, and so we multiplied by s. So one of the things we're going to want to do right away here is let's divide out. We want to isolate and frankly get s in as many of the denominator terms as we can. So if we divide by s to the 4th, right, this is going to be 6, and we like that because that's not going to be a function of a value going to 0 or infinity, plus 2 over s squared. Oops, why is that doing that? S squared plus 5 over s cubed. And we're going to be happy. Those last two terms are going to be infinity. I mean, infinity in the denominator is going to drive them to 0. All right, now in the denominator, what are we going to have here? I mean, we can kind of see the direction it's going to go. We basically want to find the s to the fourth term, right? And there will be one. But let's go ahead and we're probably going to have to pull out the denominator and make it what? S times s squared plus 4s plus 4 times s plus 3. And boy, just lots and lots of terms. We know here we're going to have an s to the fourth. So I think I'll just go ahead and tell you the terms here. I worked them out on scratch paper. Plus, so it's s to the fourth. I'll show you all the multiplied terms. Plus 3s cubed plus 4s cubed plus 12s squared plus 4s squared plus 12s. And you can sort of see where those are all going to come from. All right, we may need some of that. If we pull all this together, right, we've got s to the fourth plus 7s cubed plus 16s squared plus 12s. Okay, so that will all fit, whoops, rather than recopy it. This whole term will go back under here. It isn't going to matter because we're going to divide it by s to the fourth, right? And I'll put the divided term in here, so that's 1 plus 7 over s plus 16 over s squared plus 12 over s cubed. And you can see quite simply, as soon as s goes to infinity, all of these terms back here go away, and we're left with 6. So one of the limits is the f of 0 is equal to 6. Okay, now we'd like to find f of infinity, and that's going to be equal to the limit as s goes to 0 of s g of s. Okay, so this ought to be pretty straightforward here. All right, so in this case, we're not going to want to get the s in the denominators isolated. We don't want to isolate that front term. We're just going to go back to the original s times g of s up here. Take this whole thing, and let's divide by this freestanding s. So it's going to be 6s cubed plus 2s plus 5. So there's an isolated integer. We like that. Times s plus 2, the quantity squared, times s plus 3. And if we let s go to 0, then this goes to 0. That term goes. That's gone. That's gone. And we get 5/12. Okay? 2 squared is 4 times 3 is 12. All right. So those are the limits. And this will be it for part 2. We will finish the chapter in part 3.